Hello. Thanks for the organizers for inviting me, and thanks for the introduction. Hello, everyone. My name is Eun Jong Kim. I'm a postdoc in Professor Oscar Painter's group at Caltech. The name of our session is Superconducting Circuit-based Quantum Computing, but the work I will present today is a more physics-oriented work I've been doing for the last 2.5 years, which is on a superconducting quantum simulator based on a photonic bandgap metamaterial. The funny illustration here is an optical micrograph of the device used in our work, where we realize long-range connectivity between superconducting qubits utilizing a scalable photonic waveguide bus. This work was posted on arXiv just a few days ago, if you're interested in knowing about the details. So I would like to start my presentation by talking about various experimental platforms constructed for quantum simulation and computation. There has been remarkable progress in the last few decades, which made it possible to control individual quantum degrees of freedom, allowing us to experimentally study various topics in quantum many-body physics, and also think of realization of a practical quantum computer. The most well-known examples of this is the AMO systems with atoms trapped in optical lattices or an array of optical tweezers. Also, trapped ions and artificial quantum systems such as superconducting qubits are promising candidates for quantum computation. In many of these cases, the range of interaction in quantum processors are limited to nearest neighbor by the local nature of coupling. And examples of such cases include most superconducting quantum devices and arrays of atoms. There are various reasons why we want to pursue long-range connectivity in these type of quantum processors. One may think that short-range connectivity is not really an issue in practice because the most highly pursued quantum error correcting code, known as the surface code, only assumes nearest neighbor connectivity. However, it is known that long-range gates not only reduce the overhead of certain quantum algorithms involving non-local operations, but also the restrictions on important metrics of quantum error correcting codes. On the fundamental side, long-range connectivity enables the study of interesting quantum many-body physics, such as information scrambling and non-local spreading of entanglement beyond a light cone description. And also, addition of long-range interaction is known to break the integrability, inducing quantum chaotic dynamics. And moreover, realizing tunable long-range connectivity grants access to different physical regimes and the crossovers between them. Examples of quantum systems with long-range connectivity include cases where connectivity is realized by employing coupling to non-local degrees of freedom. For example, it is well known that in trapped ions, phonon-mediated interaction between ions can be used to generate an interaction that is characterized by the power law decay. Also, one can synthesize the connectivity by advanced control over the system. In a leading work done with tweezer-trapped Rydberg atoms, they were able to coherently transport the atoms to generate entanglement on demand. In superconducting quantum devices that I work with, a natural direction is to utilize photons for mediating non-local interactions. And in the following slides, I will provide an overview of schemes for generating photon-mediated interaction between superconducting qubits. So the most well-known scenario is the utilization of cavity quantum electrodynamics, where qubits are coupled to a common cavity at a coupling strength Gi. And in this case, the effective Hamiltonian is given by this coherent interaction with the coherent interaction Jij between all possible pairs of qubits, realizing all-to-all connectivity. And this type of interaction was first demonstrated in Rydberg cavity QED, followed by the first demonstration in superconducting circuits back in 2007. While all-to-all connectivity is good and promising, we need to ask whether this interaction mediating scheme is scalable. If we, for example, think about a Fabry-Perot cavity of size L, this is known to have resonances at frequencies that are integer multiple of this C over 2L. Therefore, if we decide to double the size of the cavity to accommodate more emitters, for example, the mode spectrum gets denser by a factor of 2. And further doubling the system size again to accommodate more emitters, the mode density that gets denser again. And therefore, it is quite evident that increasing the size of the cavity will eventually lead to the breakdown of a single mode picture of cavity QED, which is used to obtain this form of interaction. While there has been demonstration of a 20-qubit system based on this principle, it was shown that placing qubits close to each other in order to couple to a single cavity in general results in an undesired setting where parasitic near-field coupling dominates the interactions. This is basically arising from the fact that a cavity is a zero-dimensional object. To overcome this, we can imagine utilizing an intrinsically 1D scalable object, such as a waveguide, which forms a continuum of modes across a wide range of frequencies. And in a setting where emitters are coupled to a common waveguide at a decay rate gamma 1 di, it can be shown that there are two processes called the coherent exchange interaction and the correlated decay, both of which effectively have an infinite range. And this is described by this non-Hermitian effective Hamiltonian. Here, the diagonal components of the correlated decay basically corresponds to the self-decay of qubit to the waveguide, which is always present. And therefore, there are needs for fine-tuned strategies to avoid quantum information from dissipating into the waveguide channel, either by only utilizing subradiance entangled states inside a decoherent space subspace, or by killing off dissipation by multipoint coupling to the waveguide, known as the giant atom. There is also a distinct regime where quantum emitters are coupled to a photonic waveguide structure with bandgaps, something like what is shown on the right. And we can construct such a structure, for example, by periodic repetition of a dielectric medium. Now, we imagine coupling a quantum emitter to this structure at a transition frequency inside a photonic bandgap. And in this case, it was predicted by Sajeev John and Jian Huang that the emitters are dressed with photons localized near the emitter, forming a bound state. Such bound state of emitter and photon is a result of hybridization of atomic excitation with cavity-like excitation of modes inside a transmission band. And it is important to note that while the emitter itself is a local point-like object, the emitter photon bound state now has a broad spatial extent provided by the photons while simultaneously being protected from radiation. Soon after the prediction of emitter photon bound state, it was also shown that the overlap of photonic tails of bound states can be used to induce interactions between emitters. And specifically in this case, the detuning delta of emitters from the band edge frequency determines the interaction range. For example, for small detuning from the band edge, the strong near resonant hybridization of emitters with the photonic band lead to the delocalization of the photonic envelope of the bound state, resulting in long-range photon-mediated interactions. Similarly, large detuning, meaning if you're tuned deep inside a bandgap, makes the photonic envelope more localized, realizing a short-range interaction. And it was proposed that such tunable interaction range can be harnessed to realize a platform for simulation of quantum many-body physics. And this concept was first experimentally investigated in a system of atoms interfaced with nanophotonic structures, such as a photonic crystal waveguide. But however, this approach suffers significantly from technical difficulties associated with trapping atoms near photonic structures, only allowing for basic characterization. This was followed by realizations in superconducting circuits, where such trapping overhead is non-existent. In particular, qubits were coupled to arrays of on-chip microwave transmission lines, which is a microwave analog of the photonic crystal. And another approach based on a more compact and controllable design of the waveguide was pursued by our group, even realizing a novel qubit photon bound state with topological character. However, only small size systems with 1 or 2 qubits or moderate size systems with limited control was demonstrated so far. The work that I'll describe today is the realization of a scalable many-body quantum simulator with high controllability based on this idea. So the photograph here shows an example of such superconducting quantum device packaged in a printed circuit board and a copper enclosure. And from now on, I will provide the main results of our work. The basic building blocks of our simulator consists of a metamaterial waveguide, which can be modeled as an array of cavities with nearest neighbor coupling T. And this realizes a dispersion relation shown on the right with 2 bandgaps, named the lower bandgap and the upper bandgap. We imagine coupling quantum emitters to every side of this cavity array. And in this case, if we trace out the cavity degrees of freedom, we are left with effective Hamiltonian in the qubit subspace, which describes the interaction between qubit photon bound states at a rate given by Jij. And it can be shown that the Jij decays exponentially with the distance between qubits at a length scale C, determined by the detuning from band-edge frequencies, which realizes long-range connectivity between qubits beyond nearest neighbor. In particular, it can be shown that when the transition frequencies of qubits are inside the upper bandgap, the Jij is always positive with exponential decay as a function of separation. However, when transition frequencies of qubits are inside the lower bandgap, the Jij additionally collects a sign factor, alternating with increasing separation between qubits. Therefore, accessing these 2 regimes will show an interesting effect in many-body physics associated with frustration. And this generic scheme is realized in superconducting circuits by creating an array of capacitively coupled LC resonators with qubits capacitively coupled to each side. The optical micrograph shown here is the metamaterial-based quantum simulator based on the principle in the previous slide. So to summarize what is here, the device consists of 42 compact LC resonators forming metamaterial waveguide at a lattice constant of about 300 microns, which is colored blue. And each LC resonator forming the metamaterial waveguide is made of a meander inductor and a large planar capacitor. Now we zoom into the center region of the chip, and we see that we have 10 transmon qubits, colored orange, and the readout resonators in green, coupled to the 10 inner unit cells of the metamaterial waveguide. The metamaterial waveguide transitions to external 50-ohm matched input-output ports via a tapering section, which is designed to reduce the reflection at the boundary. And this tapering section is essential for reducing ripples of the transmission spectrum shown here. Here, the qubits are operated inside the bandgap of the metamaterial waveguide, and the readout resonators, indicated by these resonances, sharp resonances, are designed to be inside the passband without need for additional feed lines, realizing a resource-efficient qubit readout architecture. Also, in this case, the metamaterial waveguide itself acts as a Purcell filter, nearly eliminating the additional decay of qubits associated with a readout. Now, it can be shown that our quantum simulator can be theoretically described by an extended version of Bose-Hubbard model with long-range hopping, represented by this Hamiltonian. 2 major processes of this Hamiltonian is the on-site interaction UI and the long-range hopping Jij, not limited to nearest neighbors, both of which are tunable. Specifically, the on-site interaction U originates from the enharmonicity of transmon qubits, which takes negative values, indicating attractive interaction. And in the case of qubit photon bound states, the on-site interaction is inherited from that of transmon, where the dressing of a transmon at different frequencies modifies the value of the on-site interaction. And the tunable long-range hopping corresponds to the metamaterial-mediated coupling between qubits. And now that we have a basic theoretical understanding of the system, we may ask how we can characterize the Hamiltonian parameters that are realized in the experiment. The most basic method for characterizing the on-site interaction is to perform qubit spectroscopy after initialization into its first excited state. And if we plot the measured enharmonicity value as a function of first transition frequency of the qubit, we find the unique dependence in both the bandgaps. First, inside the lower bandgap, the dressing of the first transition with the passband mode results in a shift of the transition frequency, also known as the lamp shift. And at the same time, the 1-2 transition remains far off resonant from the passband, so this is not affected so much. And these two result in this behavior of enharmonicity, which is greatly altered close to a bandage, while deep inside the bandgap, we find a value that is close to the bare enharmonicity of the transmon that is designed. And inside the upper bandgap, there's a very strong hybridization of 1-2 transition as it's very close to the bandage, which results in a very fast drop of enharmonicity close to the bandage. And to summarize, we have achieved a very widely tunable on-site interaction. And the basic characterization of hopping terms can be also performed by 2-qubit measurements, where we induce vacuum-Rabi oscillations between a pair of qubits. And shown on the right is the pulse sequence to achieve this, where one of the qubit pair is locally excited with a pi pulse, followed by simultaneous dynamical tuning of qubits on resonance followed by projective measurement, which gives a chevron-like oscillation pattern here. And by fitting the oscillation curve on resonance, we can extract the magnitude of hopping as a function of frequency for all possible pairs of qubits in our system. Here, the topmost brown data points and fitting curve correspond to the nearest neighbor hopping of distance 1, and the bottommost yellow data point and curve corresponds to the longest hopping distance of 9. From this data set, we have realized a widely tunable hopping strength beyond nearest neighbor. We can also see that the long-range hopping plotted against the distance fits pretty well to the exponential curves, which gives the localization length C of the bound state as a function of frequency. And the realized localization length, effectively corresponding to the hopping range in the extended Bose-Hubbard model, ranges from 1.4 to 4.2. And we also note that the values of parameters measured in our experiments are quite uniform across various qubit pairs of the same distance. Now, we may say that we have fully characterized the Hamiltonian parameters, but there is still one thing left, which is the sign of the hopping terms. I have briefly mentioned that the sign of hopping is uniformly positive inside the upper bandgap, while inside the lower bandgap, the sign alternates with increasing distance. This alternating sign information cannot be determined by conventional single qubit or 2-qubit experiments. However, it can be shown that they greatly influence the many-body evolution of the system. Therefore, it is natural to ask whether we can use many-body dynamics to determine this type of information on the Hamiltonian parameters. One idea is to utilize the many-body fidelity F to guess the Hamiltonian realized in the experiment. Here, the many-body fidelity is defined as the overlap between the density operator rho realized in the experiment and the final state theoretically expected from time evolution of the initial state under the guessed Hamiltonian. And knowing this fidelity, we can in principle optimize a parameter of the guessed Hamiltonian, H prime, for example, that is parameterized by the hopping terms, to maximize the fidelity F. However, it is practically very challenging to determine F as it involves direct characterization of the density matrix through quantum state tomography, or in limited cases, a measurement of non-local observables appearing in the formal expression of F. An alternative method to achieve the same task was proposed by our theory collaborators Daniel Mark and Soonwon Choi at MIT, where the an estimator FD of the many-body fidelity can be used. So the FD compares the probability of measuring a bit string Z between the experiment and the theory after many-body evolution. And this has a lot of similarity with the cross-entropy benchmark studied in Google's quantum supremacy paper. Important thing about this fidelity estimator is that it closely tracks the true many-body fidelity F, requiring experimental capabilities of many-body quench evolution under sufficiently chaotic Hamiltonian and also site-resolved measurement in a natural choice of basis. We have experimentally demonstrated this protocol to learn about the Hamiltonian realized in our experiment. On the experimental side, we have initialized the 10 qubits in a state corresponding to the bit string Z in it, and their idle frequencies, dynamically tune them on resonance for time tau, followed by projective measurement at the original idle frequencies, which gives the measurement outcome in the form of bit string Z. And after about 10,000 repetitions of this experiment, we obtain the probabilities of measuring a bit string given by PZ. On the theory side, we perform numerical simulation of time evolution with assumed parameterized Hamiltonian, which allows us to calculate the theoretical bit string probabilities at the same time. And the pattern of experimental and theoretical bit string probabilities can be processed through this formula, FD, to obtain the fidelity estimator. And as a demonstration of this, we show the dynamics of FD when qubits are tuned to interact at 4.72 gigahertz, indicated by the dashed line on the right in the Jij versus frequency curve. Here, it is theoretically expected that the sign of the hopping terms will alternate with increasing distance. Using the Hamiltonian with hopping amplitudes taken from independent 2-qubit experiments, assuming alternating signs, we obtain the orange curve that determines the decay of FD over time. And assuming that the hopping sign is uniform and positive, however, we see that you obtain the green curve showing a much smaller FD value, indicating the theoretically expected alternating sign is favored by the higher FD. Following the same procedures, we can even perform optimization of Hamiltonian parameters with FD as a cost. And this gives this blue curve. Here, the bottom right figure shows the dependence of FD value as a function of single hopping parameter before and after optimization during the optimization procedures. And we perform independent optimization of nearest neighbor hopping amplitudes and uniform hopping amplitudes for longer distances, as shown by triangular data points with the error bars corresponding to 1 standard deviation. It is shown that the optimized parameter set agrees pretty well with the results from independent 2-qubit experiments indicated by filled circles. And more importantly, this confirms the alternating signs of hopping. Now that we have characterized the Hamiltonian parameters, we can leverage our tunable long-range connectivity to study the crossover from integrable to ergodic dynamics. So we have already seen that the interaction between qubits are short-ranged deep inside the bandgap, while it becomes long-range close to the band edge. Here we have looked at 2-photon quantum walk enabled by initializing the middle 2 qubits in their excited state and performing quench dynamics at a few different frequencies. For example, the short-range interaction achieved at 4.5 gigahertz gives 2-photon quantum walk pattern like this, showing a ballistic transport of photons as a function of time, normalized by the nearest neighbor coupling strength. While the population dynamics show qualitative behavior, we can also look at the global moments of the bit string probabilities to get some more intuition about the ergodicity of the system. For example, the global second moment mu2, which is a sum of square of all bit string probabilities, reflects the evolution of randomness across the system. And we can see that the moment starts from unity, decaying quickly to some value with some recurrences, and then eventually converges to a final value. As we increase the hopping range by moving closer to the band edge, what we find is that the initial decay to the final value becomes faster with smaller recurrences. And the final value in the ergodic limit is represented by this value mu2e, which is equal to 2 over d plus 1, where d is the dimension of the Hilbert space. And this is expected, this is a value that is expected from a random wave vector in a Hilbert space. And this is distinct from the expectation from integral dynamics shown with a dashed line, where there is no convergence of mu2 to this value. From this, we have seen our ability to realize various levels of integrability in many-body dynamics. Finally, I would like to conclude the talk by providing a summary and discussing the future directions of our work presented here. So the work presented today shows a first demonstration of a quantum many-body simulator based on a photonic bandgap waveguide, featuring a 1D scalable waveguide design and long-range connectivity, together with high controllability. And we have characterized the parameters of the extended Bose-Hubbard model realized in our system by conventional single qubit or 2 qubit measurements, as well as a novel many-body characterization. And the tunable hopping range in our system was used to show crossover from integrable to ergodic many-body dynamics. And finally, I didn't have time to touch upon this, but we have characterized the associated ergodic dynamics by looking into the distribution of bit string probabilities, where we show Porter-Thomas distribution, a signature of many-body state going through exploring all parts of the Hilbert space. And we expect that we could study a few different topics in quantum many-body physics with the quantum simulator demonstrated in our work. So the first interesting topic that utilizes the natural Hamiltonian in our system is to study extended Bose-Hubbard model. And to be specific, we can expect that the uniform sign and the long-range coupling inside the upper bandgap will make it more favorable to form superfluid phase, while inside the lower bandgap, the frustration effects come into play with alternating signs, making Mott insulator phase preferred. More quantitatively, we expect a significant change in the phase diagram of the system associated with the long-range hopping. And another natural direction is to utilize quantum chaotic nature of our many-body state realized under quench dynamics. And for example, it was shown that the ensemble of projected states of a subsystem exhibit universal randomness, giving rise to quantum state designs. Finally, there are already theoretically investigated routes to realizing various coupling profiles by using driving techniques, which could enable studies of novel interacting spin systems. And I would like to conclude the talk by acknowledging people who are involved in this work. So the experiment was led by myself and the grad student Cherry Zhang in Professor Oscar Painter's group at Caltech. And we appreciate numerous theory support from Professor Soonwon Choi and grad student Daniel Mark at MIT. And we gratefully acknowledge funding from IQIM, Department of Energy of the United States, and the Amazon Web Services. This is the end of my talk, and I'll be happy to answer any questions.
Thanks, Dr. Kim, for the nice talk. We are open for questions. Yes.
Yeah. It was a very interesting talk, and at the end of your talk, you compared with some quantum chaos. And
yes.
So have you checked the energy level spacing dynamics, space distribution, level spacing?
That's a very good question. So, one way to uncover the quantum chaos is definitely energy level spacing. There are ways to measure that by a combination of, interferometric methods, but we haven't done that in our experiment.